Hello everybody, this is Mr. Strager. Hope we're having a good day. Today we're going to be talking about the lesson 1.5 notes. Now, 1.5 is going to be all about what we're going to call literal equations. But before we get into that, I want us to do a quick little exercise together. All right? We have worked with so many different types of equations at this point throughout the semester that I bet we can solve them without even needing to use any letters or numbers. What do I mean by that? That sounds like nonsense, Mr. Strager. Don't worry. Here, I'm going to give us the following equation. Circle plus square, actually, I'll do circle plus triangle equals square. Now, these are nonsense symbols, right? They don't mean anything. Even if they don't mean anything, if I asked you to solve for a circle, meaning to get circle all by itself, could you do it? Pause the video and try it for yourself. For those who paused the video and tried it, was your step to notice that our circle is not alone, it's connected to this plus triangle, so we have to get rid of this plus triangle. Well, to get rid of plus triangle, we would subtract triangle, because that's the inverse. Despite the fact that these symbols don't mean anything, we know that to get rid of a positive triangle, you would need a negative triangle to cancel it out. So our equation would then end up being circle all by itself equals square minus triangle. Very nice. Let's take it up a notch. Let's make it just a little bit trickier. What if, starting from this point that we're at right now, I now wanted to get triangle by itself? And this one might take a couple of extra steps. So, pause the video, try it out for yourself. Hopefully you got a chance to pause the video and try it for yourself. With this equation, there are two things that are attached to this triangle. There's this square. There's no negative in front of the square, so it's just a normal square. And then there's this minus sign as well. Well, according to reverse PEMDAS, we would want to get rid of this square first, because this square is technically being added to this negative triangle. It's the same as if I had like 3 minus 2. You can think of it as 3 plus negative 2. It's the same sort of deal. So here we have to get rid of the square. Well, to get rid of a positive square, we subtract it on both sides. No big deal so far. When we do this, positive square and negative square cancel out, and we're left with this new nonsense equation. Circle minus square equals negative triangle. But we don't want negative triangle. We want to get the triangle by itself. Now, if you remember the trick with how to get rid of a negative, you could flip the sign of everything in the equation. You can just do that straight up. If you don't remember the trick, we need to think about what this negative sign is. Is it subtraction? Is it addition? Is it multiplication, division? Whenever you see a minus sign in front of some sort of variable or unknown, in this case we have an unknown, it's a triangle, it's really -1 times that unknown. That's really a -1. So how do I get rid of -1 being multiplied to our triangle? Well, we would have to divide by -1, of course. And that'll give us our triangle by itself. Here's the kick, though. We divided this entire side by -1. So do we divide the circle by -1 or the square? If you said both, you are correct. This whole side is divided by -1. This whole side has to be divided by -1. So when we simplify this side, this part's easy. The -1's cancel out, leaving us with just triangle. We got it by itself, so we know that whatever we have on the other side will be our solution. The problem is what we do with this. Circle minus square divided by -1. Any time you are dividing by -1. It's the same as if you were multiplying by -1. So what this is really saying is -1 times circle minus square. But we're multiplying the -1 to both terms. So we have to make the circle negative and this negative square of another negative. So what's the negative version of circle? It would be negative circle. You know we're talking nonsense when we start talking about negative circles in math. What about negative square? Well, a negative divided or times by a negative is a positive. So our final answer is negative circle plus square equals triangle. All right, so we've spent 5 minutes talking about circles, squares, and triangles. Where's the connection? Notice how, despite the fact that these symbols carry no meaning for us, in an equation at least, I mean, we know what a circle is and what a triangle and what a square are, despite the fact they have no meaning for us, we were still able to perform these steps. We were still able to work our way down, get circle by itself, then work our way down and get triangle by itself. This is the most important, key thing you need to know to succeed in this section and in the unit as a whole. Understanding the steps to get rid of something, no matter how complicated that something is. Everybody, we are going to see some very complicated problems with this section. Complicated looking, at least. But the steps are universal. You are always doing inverses on both sides. And as long as you can remember that, we will make it through. Let me give you another example that'll look a lot like this. Let's say instead of a circle, we had the letter X. Instead of a triangle, we had the letter Y. And instead of a square, we had the letter Z. Then this might look a little bit more familiar. What we really did is we took this equation, which we will soon learn is a literal equation, and we got X by itself. We don't know what X, Y, or Z are, but we don't need to perform the steps. Even though we don't have any numbers in this problem, we still know that if you want to get rid of positive Y, you subtract Y from both sides, giving us X equals Z minus Y. Circle equals square minus triangle. Or if you want to take it a step further and try to get Y by itself, well, you know there's a Z here, so we have to subtract the Z from both sides, giving us X minus Z equals negative Y. And then what do we do in our problem to get rid of that negative? We divided both sides by -1, giving us negative X plus Z equals our positive Y. Again, this is the essence of literal equations, saying that no matter what is on the paper, no matter how complicated it looks, I can deal with it as long as I know the steps. So let's flip back to our notes. These are on page 24. And let's talk definitions for a moment. The definition of a literal equation is this. A literal equation is an equation with two or more variables. Here's the deal about when you have an equation with two or more variables. At least at this point in our math careers, you cannot get something like x equals 2 when you have an equation with two variables. Because, unfortunately, you're never going to be able to simplify that other variable. Your answer, if you wanted to get x by itself, would be something like this, where all of your other variables are on the opposite side. That's the only way you're going to get this variable by itself. It looks almost unsolved, but that's why it's so important that you remember what you can and cannot combine. 2 plus y is not 2y. 2 plus y, you can't add them together. The other bit of vocabulary that we are doing for this section is with the term formula. Now, the word formula means many different things in many different subjects. In math, a formula is a literal equation. So it's a type of literal equation that shows the relationship between all variables. That shows the relationship between its variables. Excuse me. What I mean by this is, if we look back at the equations we wrote down, this is nonsense. This means nothing to us. We understand that there's an x, a z, and a y, but we don't know what any of these variables mean. They're just letters on a page. If I gave you something a little bit different, let's say I gave you this, a equals 1/2 bh. Does that sound familiar? If it doesn't sound familiar, take a couple of seconds, pause the video, and try to think about what this is. You may have realized this is the formula for the area of a triangle. And these letters actually mean something to us. A represents the area. B represents the base. And H represents the height. Each of these variables means something to us, and because of that, we can see the relationship between them. We see that the base times the height times something else will make the area. The relationship between the base and the height is that you multiply them to get the area. That's the difference between a formula and a literal equation. So, are we ready to try one? Let's try a literal equation together. And again, we kind of already did a literal equation with the circles, squares, and triangles. It's just that this one is going to have our usual numbers and variables in it. So let's say I gave you the equation. 3y plus 4x equals 9. Now, many of you might just get started and try this one out and get an answer. But there's a problem. We have two variables here. And I never told you which variable we want to solve for. Keep in mind, you could choose to get x by itself, or you could choose to get y by itself. You won't need to solve for every variable in a literal equation, just the one you're asked to solve for. In this case, to mix things up, I actually want you to solve for y. Whenever you see the word solve for a variable, you know that that just means to get that variable all by itself at the end of your problem. So our end goal is to have y by itself. How can we do it? Take a minute or so, maybe a little longer, and try this one out. Did you try it? If not, take a look at this. We want to get this y by itself, but there are some things that are attached to it. One of them is this 3 here. Anytime there's a number next to a variable, they're being multiplied. The other part is this plus 4x. So we're eventually going to need to get rid of them, but which one do we get rid of first, the 3 or the plus 4x? Well, those who remember their PEMDAS rules know we want to get rid of the addition or subtraction first. So to undo plus 4x, we subtract 4x from both sides. These cancel out, and that gives us 3y equals 9 minus 4x. So far, so good. Your equation probably won't get much shorter, unfortunately. It's still about the same length as this. But your y will get closer and closer to being alone, and that's how you know you're in the right direction. So how do we get 3 by itself? Well, if you said to divide by 3 on both sides, you're correct. But again, we face that same problem that we saw with our circle, squares, and triangles. Do we just divide the circle or the square? Well, we chose to divide both because it's this entire side divided by this entire side. So, we divide this entire side by 3, we have to divide this entire side by 3, meaning we're going to make a big fraction with it. But these 3's cancel out, your y is by itself, and you end up with this mess. 9 minus 4x divided by 3. Now this answer is, by all stretches, correct. This is one version of the answer. But there is a way to make this simpler, and I think many people who saw this when they were trying the problem might have caught it. Whenever you have 2 numbers on top of a fraction divided by 1 number below, what this really is saying is 9 over 3 minus 4x over 3. You can split it into 2 fractions with the same denominator. It's like if I had the fraction, let's say, 5 minus 3 over 2. Well, we know that this is going to be 2 on top. 2 over 2 is 1. But you could also split it. 5 halves minus 3 halves. What's 5 halves minus 3 halves? That's still 2 halves. That's the same thing we got up here. So you split your fraction, and notice that 9/3 can be simplified. What's 9 over 3? It's 3. This is the answer that Big Ideas would want you to put in. 3 minus 4x over 3. Simple enough, right? Let's try just one more. This will be the last problem we do for this. In fact, for this unit. So, hold out, we are almost there. This last problem, though, is going to teach us quite a bit. Because with literal equations, sometimes we need to use some, shall we say, unorthodox methods to solving them. Before I give you the full equation, I just want to start off by giving you this. Whoops, not 3, it should be a 5xz. 3x plus 5xz. My question to you is, can we simplify this? Now, you might be tempted to say yes, because we have an x here and an x here. But remember what I said all the way back in section 1 about variables combining with each other. I'm going to make a quick table of additions, meaning you can imagine the left being added to the right. If we tried doing x plus x, well, they're the same variable. X plus x can combine to make 2x. That's fine. If I tried doing like 2 plus x, though, well, these are talking about 2 different things. The variables are not exactly the same. 2, you can think of as 2 tennis balls. X, you can think of as 2 soccer balls. Or, sorry, a soccer ball. 2 tennis balls plus a soccer ball does not make 3 tennis soccer balls. So we can't put those together. It's the same if I had an x and a y. They're 2 different variables, so you can't combine them. When we have x and xz, this is the trickiest part to remember. This is considered different than this. It's because if we're trying to add these together, right, x plus xz, let's pretend instead that x is actually 2. What that'd really be is 2 plus 2z. Could we add these? No! This is 2 and this is a z. It's the same thing when you have multiple variables in the same problem. You can't combine them. These are considered 2 different terms. X is one variable, xz is another variable, at least for our purposes in this unit. So, we cannot simplify this like that. I want you to try to figure out a way to solve this for x, but I won't have us solve it on our own, because there's an important thing that you might not have learned yet. Here's the deal. We have talked about so many inverses on this journey through Unit 1. The opposite of addition is subtraction. Subtraction is addition. The opposite of multiplication is division. The opposite of division is multiplication. We even talked about the opposite of absolute value in our last notes. And we said the opposite of absolute value is splitting, which isn't really an operation, it's more like a process. Well, now we are going to talk about the last inverse for this unit. It's another process. The opposite of distributing. Now you remember distribution. Whenever there's a number outside of parentheses, you can multiply it to all the things inside the parentheses. The opposite of distribution is what's known as factoring. And factoring is where you take two of the same thing, whether it's two x's or two 2's or two -5's, and you pull them out from both terms and put it back in front. Notice how this is 1x being turned into 2. Well, this is 2x's being turned into 1. For instance, if I had this distribution to do, x times the quantity 2 plus y, well, to distribute, we would take this x, we'd multiply it to the 2 and multiply it to the y, giving us 2x plus xy. But let's say we wanted to go back on that. Let's say we say, ooh, I messed up, I didn't really want to do that. Well, the opposite of distributing is factoring, where we take a common factor, something that both numbers have in common, or both terms have in common, and pull it right back out and put it in front. What that means is we can take an x out of both of these again, put it in front, we'd be left with 2 plus y, but we don't want this to seem like it's just x times 2. That wouldn't be right. We have to put our parentheses back around it. Again, it's the opposite of distributing, is pulling it out and making a problem that has parentheses and something multiplying. So what can we factor out of this equation? It's the x. There's an x here and an x here. If we pull both of them out from their respective terms, what are we left with? Well, our y on the other side won't change, but we'll have our x over here. We'd have to put up our parentheses, because that's how we bring it back to a distribution problem. And what would we be left with? Well, when you take out the x from this left term, you just have 3. When you take out the 5z from this right term, when you take out the x from this term, you're left with 5z. There we go. That's what I was trying to say. So this is what we're left with. Notice now that our x is all alone. Even though we couldn't combine these terms, now we're back to 1x. And whenever there's just 1x, we know how to solve that. Remember what I said at the beginning about the problems looking crazy, but as long as you remember the steps, you can always apply those steps, no matter what the numbers are. Here, this is x times 3 plus 5z. Try not to concentrate on the fact that it's 3 plus 5z. That's a crazy mess. If you focus on that for too long, you'll go nuts. Instead, focus on what can we do to get x by itself. X is being multiplied to 3 plus 5z. So how do we get rid of the 3 plus 5z? We divide by 3 plus 5z. I told you it was going to look like nonsense. But we don't care what this term is. We don't care about what's in the parentheses. It could be a string of 1,000,000 numbers long. It could be something crazy complicated. What we care about is it's being multiplied to the x. So to get rid of it, we divide it. thinking about the process is how we solve these problems. Because now, these 3 plus 5z's, they cancel out on this side. We've got just our x by itself. And what's on the other side? Well, y divided by 3 plus 5z. And this can't be simplified any further, right? There's nothing we can combine. So, you know what that means? It means that this, even though it looks messy, is our answer. This is the essence of literal equations. Looking at the steps you would normally do, no matter how ridiculous a problem seems, no matter how many variables there are, just doing the same steps and leaving your answer as maybe a little bit messier than you would expect. All right, everybody. Have a great rest of your day. See you next time.